When dealing with multiple service disconnects, it's important to understand the proper grounding requirements to ensure electrical safety and compliance with the National Electrical Code, or NEC. The question of whether it's acceptable to run grounding electrodes to the first service disconnect and then use a jumper to connect to other service disconnects is addressed directly. The answer is no, this is not an acceptable practice. Each service disconnect must have its own connection to the grounding electrode system. The NEC specifies that the grounding electrode system must be connected to each service disconnect. This system typically includes electrodes such as a ground rod, ground ring, metal water pipe, or concrete encased electrode, also known as a UFA ground. The purpose of the grounding electrode system is to provide a low impedance path to ground, helping to stabilize voltage during normal operation and providing a path for fault current to flow back to the source, allowing overcurrent protective devices like circuit breakers or fuses to trip and clear the fault. The NEC section 250.24 addresses grounding service applied alternating current systems. This section requires that the grounding electrode conductor be connected to the grounded service conductor at the service equipment or as specified in 250.24. This connection ensures that the system is properly grounded and that fault currents can flow back to the source. Now let's elaborate on why a single grounding electrode connection with a jumper to other service disconnects is not acceptable. Firstly, this method can create a high impedance path for fault current. The jumper wire, even if it's sized appropriately, introduces additional resistance and inductance into the grounding path. This increased impedance can impede the flow of fault current, delaying the tripping of overcurrent protective devices. Secondly, relying on a single grounding electrode connection can lead to unequal voltage distribution among the service disconnects. During a fault, the voltage drop along the jumper wire can cause voltage differences between the disconnects, potentially damaging equipment connected to the ungrounded disconnect. Thirdly, the NEC specifically requires each service disconnect to be grounded independently. This requirement is in place to ensure that each disconnect has a reliable and low impedance path to ground. The code is designed to provide the highest level of safety and redundancy. To properly ground multiple service disconnects, follow these steps. 1. Identify all service disconnects. Determine the number and locations of all service disconnects in the system. Each disconnect will require its own grounding electrode conductor connection. 2. Establish the grounding electrode system. The grounding electrode system must consist of one or more of the electrodes specified in NEC section 250.52. These may include a metal underground water pipe, a concrete encased electrode, a ground ring, or ground rods or pipes. 3. Connect each service disconnect to the grounding electrode system. Run a grounding electrode conductor from each service disconnect to the grounding electrode system. The size of the grounding electrode conductor is determined by NEC table 250.66 based on the size of the service entrance conductors. 4. Bond the metal enclosures and equipment. Ensure that all metal enclosures containing service conductors and equipment are properly bonded together and connected to the grounding electrode system. This bonding helps to create an equipotential plane, minimizing voltage differences and reducing the risk of electric shock. It's crucial to understand that the NEC provides specific guidelines for sizing the grounding electrode conductor. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Table 250.66 in the NEC provides the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. For example, if the service entrance conductors are 4/0 American wire gauge copper, the minimum size of the grounding electrode conductor to ground rod or pipe is 6 American wire gauge copper. However, if the grounding electrode is a concrete encased electrode or a ground ring, a smaller size may be permitted. Always refer to the latest edition of the NEC for the most up-to-date requirements. In addition to grounding electrode conductors, bonding jumpers play a crucial role in ensuring electrical safety. Bonding jumpers are used to connect metal enclosures, raceways, and other non-current carrying metal parts to the grounding electrode system. This bonding helps to create a low impedance path for fault current, reducing the risk of electric shock. NEC Section 250.92 specifies the requirements for bonding service equipment. This section requires that all service equipment enclosures be bonded together and connected to the grounding electrode system. The size of the bonding jumpers is determined by NEC Table 250.102, based on the size of the service entrance conductors. Proper grounding and bonding are essential for electrical safety. They help to protect people and equipment from the hazards of electrical shock and fire. By following the NEC requirements for grounding and bonding, you can ensure that your electrical system is safe and reliable. It's always recommended to consult with a qualified electrician or electrical engineer to ensure that your electrical system meets all applicable codes and standards. Let's consider some common scenarios and examples to further illustrate the importance of proper grounding for multiple service disconnects. Scenario 1. A large commercial building has two separate service entrances, each with its own service disconnect. In this case, each service disconnect must have its own connection to the grounding electrode system. You cannot run a grounding electrode conductor to one disconnect and then jump to the other. Each disconnect needs its independent connection to ensure that each has the required lower impedance ground path. Scenario 2. A residential dwelling has a main service disconnect and a separate disconnect for a detached garage or outbuilding. Again, both disconnects must have their own grounding electrode system connection. The garage disconnect cannot rely on a jumper from the main house disconnect. This ensures that the garage has its own independent ground, minimizing the risk of voltage differences and providing a proper fault current path. Now let's address some specific components of the grounding electrode system. Ground rods are a common and relatively inexpensive grounding electrode. When using ground rods, it's important to drive them deep enough into the earth to ensure good contact with the soil. The NEC requires that ground rods be at least 8 feet long and driven at least 8 feet into the ground. If multiple ground rods are used, they should be spaced at least 6 feet apart. Concrete encased electrodes, often called UFA grounds, are another effective grounding electrode. These electrodes consist of at least 20 feet of bare copper conductor encased in concrete that is in direct contact with the earth. UFA grounds are commonly used in new construction and provide excellent grounding due to the large surface area in contact with the earth. Metal water pipes can also be used as grounding electrodes, but they must be supplemented by another electrode, such as a ground rod or UFA ground. This is because plastic water pipes are becoming more common, and the metal water pipe may be replaced with a plastic pipe in the future, which would eliminate the grounding path. In addition to the grounding electrode system, the equipment grounding conductor plays a crucial role in electrical safety. The equipment grounding conductor is a conductor that connects the non-current carrying metal parts of electrical equipment to the grounding electrode system. This conductor provides a low impedance path for fault current, allowing overcurrent protective devices to trip and clear the fault. The equipment grounding conductor must be sized according to NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. It is essential that the equipment grounding conductor is properly installed and connected to all metal enclosures and equipment. Understanding the differences between grounding and bonding is crucial for proper electrical system installation. Grounding refers to connecting the electrical system to the earth, providing a reference point for voltage and a path for fault current. Bonding refers to connecting non-current carrying metal parts together to create an equipotential plane. Both grounding and bonding are essential for electrical safety, but they serve different purposes. Grounding stabilizes the system voltage and provides a path for fault current to flow back to the source. Bonding minimizes voltage differences between metal parts, reducing the risk of electric shock. In summary, while grounding connects the system to the earth, bonding connects metal parts together. Moreover, when dealing with sensitive electronic equipment, it may be necessary to provide additional grounding and bonding measures. Sensitive electronic equipment can be susceptible to damage from voltage transients and noise in the grounding system. To mitigate these risks, it may be necessary to install dedicated grounding electrodes and isolated grounding systems. A dedicated grounding electrode is a separate grounding electrode that is used solely for sensitive electronic equipment. An isolated grounding system is a system in which the grounding conductor is isolated from the metal raceways and enclosures. These measures can help to reduce noise and voltage transients, protecting sensitive electronic equipment from damage. It's also crucial to consider the impact of harmonics and the grounding system. Harmonics are distortions in the alternating current waveform that can cause excessive current flow in the neutral conductor and the grounding system. These harmonic currents can overload the neutral conductor and the grounding system, leading to overheating and equipment failure. To mitigate the effects of harmonics, it may be necessary to install harmonic filters or to oversize the neutral conductor and the grounding system. Harmonic filters are devices that reduce the amount of harmonic current in the system. Oversizing the neutral conductor and the grounding system can help to accommodate the additional harmonic current. Finally, remember that electrical codes and standards are constantly evolving. It's essential to stay up to date on the latest requirements to ensure that your electrical system is safe and compliant. Always consult with a qualified electrician or electrical engineer to ensure that your electrical system meets all applicable codes and standards. Proper grounding and bonding are crucial for electrical safety, and it's important to understand the requirements and best practices to protect people and equipment from the hazards of electrical shock and fire. When working with multiple service disconnects, each disconnect must have its own connection to the grounding electrode system. A jumper from one disconnect to another is not acceptable. This is a critical safety requirement that must be followed to ensure the safety and reliability of the electrical system. In conclusion, the NEC mandates that each service disconnect in a system with multiple disconnects have its own independent connection to the grounding electrode system. This requirement ensures a low impedance path for fault current, equal voltage distribution, and overall electrical safety. Relying on a single grounding electrode connection with a jumper to other disconnects is not permitted. Proper grounding techniques, including correctly sized grounding electrode conductors and bonding jumpers, are essential for protecting people and equipment from electrical hazards. Always consult with a qualified electrician or electrical engineer to ensure compliance with the latest edition of the NEC and local regulations. By following these guidelines, you can create a safe and reliable electrical system.